Good evening, everyone. I welcome you to the sixth week of problem solving session for NPTEL course Combinatorics. Okay, so this message is this message directly for the students who are enrolled in NPTEL course. Please please attend these lectures. We'll be solving some problems, and if you haven't caught up, like if you're not attending because you haven't done any of the previous weeks, so you can mention it in the forum, or like you can attend the classes and we'll discuss the problems from previous weeks also. So please make use of this opportunity and attend the session. Okay, so today in week 6 we'll discuss ordinary generating functions and exponential generating functions. So these functions are basically used to solve some recurrence relation. So today we'll be solving few problems which will be using ordinary generating functions or exponential generating functions. But before solving this problem, we'll quickly recall what all these are so that we know where in which problem which type of function should we use, ordinary ones or the exponential one. So firstly I'll define what are ordinary generating functions. So suppose an denotes the number of ways to build structures of type A on n set, and if Bn is denoting number of ways to build structures of type B on n set, then the power series of this form Ax where is equal to a0 plus a1x plus a2x square and so on, where the coefficient of xn is an, coefficient of x raised to power is n is an. This kind of function is an ordinary generating function. So ordinary generating function is kind of recording the data of this sequence a1 a2 a3 and so on. And similarly we have so now suppose we have two ordinary generating functions ax and bx whose nth where coefficient of xn for ax is an and for bx it's bn. Now now if we have two ordinary generating functions ax and bx, so what will be the product is like, so we are basically multiplying both these power series. Now if we are multiplying both these power series and then cx is also a power series, but now we want to see what is the coefficients of cn with respect to coefficients of a and coefficients of b. So you see, so this is basically a term like a0, this is basically a0 plus a1x plus a2x square and so on, and this is b0 plus b1x plus b2x square and so on. So now if we want to find the coefficients of this, so what is the coefficient of what is the coefficient of x0, which is 1, is basically the constant term. So how can we we are multiplying these two series, how can we obtain a constant term when we multiply a0 with b0? So c0 is just a0 b0. Now what is c1? C1 is the coefficient of x in this product. So how can we obtain x? We can obtain x basically by xi plus xj, where I plus j is equal to 1. So basically we can obtain x either by multiplying a0 with b1x and a1 with b0. So we see that C1 is a0 b1 plus a1 b0, and similarly we can generalize this and we get that coefficient of xn in Cn is nothing. So if we want to find the coefficient of xn, which is Cn, in terms of this, what is this? So basically we take some xi, ai xi, bj xj, such that xi plus xj, such that I plus j is equal to n. So we see this is the coefficient of Cn. So now this was this. So now what does this product combinatorically mean? What do we mean by this product? So an was counting the number of ways to build structures of type A on n set, whereas bn was counting the number of ways to build structures of type B on n set. Now we want to see what is this Cn what is the Cn calculating combinatorically. So we see, so if we are calculating Cn, we are basically summing it over I plus j equal to, we are summing it over I plus j equal to n, ai, the sum of terms are going from this. So this, so number of solutions of I plus j equal to n, we can see, so if we have some n set, base n set, number of solutions of this, number of solutions of I plus j equal to n, this is in 1-1 correspondence with, this is in 1-1 correspondence with dividing this n set into two intervals of this type, 1 till I and I plus 1 till I plus 1 till n. So we see that any, so if I plus j is equal to n is a solution, we can consider the partition of n as 1 to I and I plus n. But here this is a special kind of partition. This is not, this is a special kind of partition of n. So we are considering, we are not considering all possible partitions. We are only considering the partitions in the intervals. So we are basically, so what we are doing, we are taking, we have n things which are lying in a sequence, and we are taking the first half and second part. So it is not calculating all the partitions of n into two part. It is just calculating, it is in a way calculating if we have n people standing, so we are splitting that line into two places, or we are splitting this set n into two intervals. So this is what do we mean by this. And then we have ai bj. So we have this set, so we have got, so once we do this, we have got, so we have basically divided n into two intervals, say a1 and a2. Now ai and bj. So we see that order of ai is I, and order of a1 is I, and order of 2 is n minus I, which is j. So we see when we are multiplying it by ai bj, this refers to, we are applying structure A on our first set a1 and structure B on our second set a2. So combinatorically, product of two ordinary generating functions, what it is calculating, if an is the number of ways to build structures of type A, and bn is number on n set, and bn is number of ways to build structures of type B on n set, then combinatorically Cn is counting number of ways to first we divide this n set or into two intervals, say 1 to I and I plus 1 n, and then we apply structure A on the first interval and structure B on the second interval. So this is our product. And in general, if you have n generating functions, say a1, a2, an, you have these n ordinary generating functions, product of this, you can check, it will count dividing this n set, if you have, k. So product of this, see, if cx is product of these k generating functions, you can check that Cn is basically counting, you are dividing this n interval n into k intervals, and mind it, these intervals can be empty also, so you are dividing it into k intervals, then applying structure a1 on the first interval, structure a2 on the second interval, structure a3 on the third interval, and so on. So this is this. Now composition of, so this was what do we mean by product of ordinary generating functions, and now we have composition of ordinary generating function. So here also we are given two ordinary generating functions, ax and bx, but here for one of these ordinary generating functions, we are assuming a naught to be 0, and we'll see why we need a naught to be 0. Now we are taking the composition of ordinary generating functions. So if we calculate it algebraically, we'll get this. So we'll get this, and so basically we are replacing, if we are replacing each x by ax. So we'll get this. Now if we want to compute the cx, now so this will give us another power series, and now we want to calculate the coefficient of c0, c1, c2, and this, now you can see that this coefficient c0, c1, c2, these are finite. We can guarantee they are finite if we assume a0 is equal to 0. If a0 is non-zero, then we cannot, then these ci's won't be finite. Therefore the cx won't be a power series. Hence we are assuming that a0 is equal to 0. So now once we have got this, once we have written it down, now from this expression, if we want to calculate what is our cn, what will it be? So basically each terms are looking like this. So we have v1 this. So we'll see the contribution coming from each of these terms. So suppose I fix my k, bk. So so the other term here appearing, so if I fix my k, say bk, the other term appearing is a1x plus a2x square, so on till raised to the power k. Now we want to see in this term what is the coefficient of xk. So what will be the coefficient? So we are multiplying this. So we are multiplying this power series k many times. So what will be the coefficient of xk? It will be basically the coefficient of xk. We'll sum it over all these solutions, because we are looking. So if we want to, we are looking at the coefficient of xk will be basically ax1, axk, where we have x1, x raised to the power xk, and this since we are looking at coefficient of n, this should sum to n. So we see that our cn is this term, that is bk. Then we are summing it over all the compositions of n, and mind it, we are taking compositions, not weak compositions, because a0 is equal to 0. So each of these xi have to be strictly greater than 0, and we are summing it over composition of n, and then we are getting ax1, ax2. This is the term. And now we see if a0 was non-zero, then we couldn't guarantee that these xi's should be then this sum will sum over weak compositions, and we know set of weak composition of n is infinite. So we are here having an infinite sum. Hence we cannot guarantee that the cn will be finite. Hence we are taking in the series that we are composing, whose constant term should be 0, to ensure that the cn is finite. So now once we have this composition, now we want to see what does this mean combinatorically. So combinatorically we see, since we are summing it over compositions of n, combinatorically it is counting that if we have some n objects lying in a line, or we have some n objects, n people standing, then we are splitting that line at various places, and these so basically if we have this line, we are splitting it at various places, and therefore we get some sublines, and these all sublines are non-empty. Then we are applying structure A. So we are structure A individually on each of these sublines, and then we are applying structure B on set of these sublines. So if we want to do that, we see that this is the, so if we want to calculate this basically corresponds to this term, because first if we are splitting a line of objects people into various places on empty lines, this basically corresponds to step A counts number of compositions of n. Now once we have split it, so once we have this splitting, then we are applying structure A on the set 1 whose order is x1, structure A on each of these sets, so which will be and x1, x2, xk are the x1, x2, xk refers to the number of people in these sublines, and since they are non-empty, these are greater than 0. And then we are applying structure A on each subline. Therefore, applying structure A means basically, since the number of people is x1, it is ax1 and ax2, and hence we get this product, this term. And now then we are third step is we have to apply structure B on set of sublines, and now the set of sublines have k elements. Therefore, this bk term is appearing. So we see that this Cn is combinatorically counting this term. Now, ordinary generating functions are generally used to solve linear recurrences. That means we are looking at recurrences of this type, and coefficient of each of these terms is constant. But now we could have some recurrence equation in which these are not constant. Therefore, we need some. So if we want to solve them, some of them can be solved through exponential generating functions. So in your class lecture, you saw an example of a recurrence relation which couldn't be solved because one of the coefficients was coming out to be n, and it could be solved using exponential generating function. So now, what are exponential generating functions? So here also the data remains same. Now so this is also, in exponential generating functions are also recording the sequence a1, an, b1, bn. The difference is that instead of using xn, we are using xn by n factorial. And if we are recording our sequence in sequence of this type, then we call this function as exponential generating function. Now we see, once we have these sequences, the combinatorial meaning of product and composition changes. So we'll see what that means. So we'll proceed similarly. So if first we see algebraically what we are getting the product term. So if px is the product of these two exponential generating functions, and pn is the coefficient of x raised to the power n by n factorial, then what is pn algebraically? So we are basically multiplying these two terms. Now we are doing the same thing, except that, so first let's calculate the coefficient of xn. So using the same trick previously, we see the coefficient of xn will be just I plus j equal to k, and here coefficient of x raised to the power I and coefficient of x raised to the power j. And what is the coefficient of x raised to the power I? It is just ai by I factorial, and coefficient of x raised to the power j is bj by j factorial. So now we see that this is this term. So we see that Pn is this. So this is this term. Yeah. So we get that coefficient of xn should be this. But we have to find the coefficient of xn by n factorial. So we'll coefficient of xn coefficient of xn is this. And so if we want to find the coefficient of xn by n factorial, it will be just, we are kind of multiplying and dividing n factorial by both sides. So we get that coefficient of n factorial will be this, the coefficient of xn multiplied by n factorial. Now once we have this, we see that this is, if we open this up, we can take this n factorial inside, and we are left with n factorial divided by I factorial j factorial, and this will be nothing but n choose I, because j is equal to k minus I. K minus, this should be I plus j equal to n. Sorry, I plus j equal to n. And since j is equal to n minus I, we see that this is, so we get the product term is n choose I, ai, bi. So combinatorically what we are counting, so first n choose I, basically we are choosing a subset x of n, and we are summing it over this. So in a way we are first, so this is combinatorically counting. First we are choosing a subset x of n, then we are applying structure A on x and structure B on x complement. And similarly, if we have k products, so what we are doing, we are kind of partitioning one n into k parts. These parts can be empty. Then we are ordering those k parts, and then we are applying a1 on the first part, a2 on the second part, and ak on the kth part. and these two steps moreover have one correspondence with choosing ordered. These two steps basically we are choosing ordered partitions of n. And if we want to choose ordered partitions of n, it is you can see this will turn out to be just n I1 ik, where I1 plus I2 plus ik is equal to n. So if we want to choose ordered so first two steps are we are kind of choosing ordered partitions of n. Why do we need ordered? Because here order matters, because these functions are different, and first we have to apply on the first set we have to apply a1, on the second set we have to apply a2, and on the kth set we have to apply ak. Therefore order matters. So if you want to find ordered partitions of n, it is in a way same as first you choose a subset, and it is same as choosing first a subset. If you want to n choose I1 ik, when you open it up it looks like n I1, n choose I1, n minus I1 choose I2, and so on till n minus I1 minus ik minus 1. Last term is n minus I1 minus I2 minus ik minus 1, choose ik. So we see, so you see that this is basically doing that. Okay. Hi.
Hello.
So I was so I was recalling the ordinary generating functions and exponential. I recalled ordinary generating functions and exponential generating functions because I wanted to like solve some problems. So are you aware of these?
You carry on, man. I'll go through afterwards. No
Okay.
problem. Yeah.
Okay, fine. Yeah. So like first I'm finding out the now. So we saw right we saw what do we mean by product of exponential generating functions combinatorically. Now we see, now next thing is we want to see what do we mean by composition of exponential generating functions combinatorically. If we do the same computation, we see that combinatorically, so if ax is basically ax is a1x plus ax is the exponential generating function corresponding to the sequence a1 a2 an, where an is counting the number of ways to apply structure a on n set. Now, and bx is recording the sequences bn corresponding to structure b. And now once we compose bax, we see that this composition algebraically looks like this. Now we want to see algebraically first of all what is the first we want to compute this coefficient cn in terms of ais and bis. So what will be cn? So we are composed. So first we are so if you want to find, so we have this term b0 plus b1 this. So now if you want to compute cn, first we are looking at its contribution from each of these bk's. So if I fix my bk, say if first I am calculating my contribution of coefficient of xn from this term bk by k factorial, and here we have sigma an xn by n factorial, which we are multiplying by k times. So if I want to compute the coefficient of this, coefficient of n from this term, so what will it be? Bk by k factorial will be as it is. And now we want to compute the coefficient of n. So let me look. So if I'll write it as ai, because I'm computing the coefficient of this. So now if I want to compute the coefficient of this, so this is basically it will be ai by product of ai by I factorial okay. Yeah. So I'm saying, yeah. So if I want to compute the coefficient, this will be basically product of ai by I factorial and xi, product of I1 by xi1, such that these I1s sum up to these I1.
Your screen is not visible.
Oh, okay. Uh, is it visible now?
Yeah, now I can see.
Yeah. So this is so we see that the coefficient is basically computing this. So so what I am doing is I am computing the coefficient of x raised to the power n, which is coming from this term. So bk by k factorial will be as it is, and here we will have some. So we have to choose one term from each bracket, so it is if it is basically choosing like xij. From each bracket we are choosing this term, and the sum of these ij should turn out to be n. Then only this will be the coefficient of n. So we see that this cn is coming out to be, we are summing it over, first we are summing it over compositions of n, since the coefficient of x raised to the power xi in each of these bracket is axi by xi factorial. So this is this term, and then this is bk by k factorial, and then we are summing it over all k. So do you understand how we are getting this coefficient?
Yeah, understood.
Yeah. So now we open it more up. So we see that, and we have this n factorial appearing, and we have this x1 x1. So we take these common. So we see that this term, so all, if we club up all these factorial terms, this will come out to be n, choose x1 till xk. If we club all the factorial terms except the k factorial term, because these are x1 factorial, so the terms appearing in the denominator are x1 factorial, x2 factorial, x3 factorial till xk factorial, and these are summing up to n. So we see that this factorial quantity is this n, choose x1 comma till xk. Now what is this term combinatorically counting? So we see that this is first composition of exponential generating functions combinatorically is counting that first we are partitioning n into non-empty blocks, then we are applying a into, so we have this set n, we are partitioning into non-empty blocks, then we are applying a on each block, and then we are applying b on set of blocks. So this term is basically counting that. So now see, so this is the difference between exponential generating function and ordinary generating function. So when we were at ordinary generating function, so if we are composing a, so if we are doing bax, so when we are in ordinary generating function and composition, here instead of splitting, so here also we had this n set. So when we are using ordinary generating function, we are splitting n into intervals. Here we are splitting n into intervals, that is here we are so if we have this 1 to n, we are only allowed to do something like 1 till I plus 1 till some j plus 1 till n. So it's in a way we have some n line of people standing, and we are splitting those lines. So in ordinary generating functions, we are considering this partition of n into intervals. But when we are at exponential generating functions, we are considering partition of n every possible partition. So this is the major difference between the ordinary generating function and exponential generating function. So now we'll solve some problems and we'll see which function can be used where. So now first problem is that we have we are given that so we have n soldiers of a military squadron which are standing in a line. Then the officers split the lines at several places, forming smaller non-empty units. Then he chooses a possibly empty subset of newly formed units for the night duty. In how many ways can this be done? So what is in this question, what we are required to calculate, we are required to calculate the following numbers of v. So what we are doing, first step is that we are splitting this line of n soldiers into small non-empty units. So we have these n soldiers which are standing in line. We have these n soldiers which are standing in this line. So first is we are splitting them into some non-empty intervals, and then what we are doing is then we are choosing a subset of newly formed units for night duty. Then we are applying some function on the set of the interval, set of the these intervals. So in this question which function should we use?
Exponential.
Why exponential?
Because the arrangement will also. No. Just a second. No. It's ordinary, not
Yes.
the exponential.
Yes, ordinary generating function, because order doesn't matter.
If the arrangement, if it matters, then it will be exponential.
Yes, very good. So now we have to use the ordinary generating functions. Correctly said. Now if we have to use the ordinary generating functions, what are the functions? So ordinary generating functions and composition. So we have this BAX. So if we have this, AX is basically the function which corresponds to structures applied on each subline, right? On each interval basically. And BX corresponds to function. BX is the function which is corresponding. BX is the function which corresponds to structures that need to be applied. On set of intervals. So in this case, what is our A and what is our B? So first we are looking. First we are looking at the function that we are applying to each of the line. So in this question, we are what we are doing, first step is we are splitting these n people into some sublines. We are splitting this line of people at various places, and these lines and each of these sublines are non-empty. And second is we are choosing a subset of newly formed line. So what is the function corresponding to AX? That is what are we doing on each of the line, on each of the subline? Hello?
Hello.
Yeah. So what do you think should be our AX?
AX means all the degrees which we can have from starting from x raised to the power 0 to x raised to the power n.
Yeah. AX. So basically, AX is. So if we have these composition, AX corresponds to AN raised to x raised to the power n, where n is greater than 0. And what is this function? So what is this AN in this composition? This AN is counting. So this AN is some ordinary generating function. So this AN counts number of ways for some n set, right? So when we are using composition of generating functions, so in this we saw earlier this AX, so when we have composition of ordinary generating functions, so what is Cn counting? Cn is counting here. Basically, we are splitting this line of objects into various places. Then we are applying structure. So AX size or these ANs basically corresponds to structure A, which we have to apply on each subline, whereas B is the function or the structures which we have to apply on the set of subline. So when we have some problem like this where we have to use composition, so we have to identify two functions. There is one function which is so there is one function which is happening to each individually to each of these lines. That function is our ax, and then we have another function which is happening to the number of lines that we have breaked this our original line into, and that function is bx. So in this question, first we are splitting this line of n people into smaller units, and then we are choosing a subset of newly formed units. So first of all, see, so so in this case we see that we are doing nothing. We are doing nothing to each of these subline, right? So first let's identify what is bx. So bx is the function which is happening to the set of lines, set of the newly formed units, or set of the newly formed units. So what is bx? So bn is basically bn is what is happening to the set of lines. So our first step is that we are splitting line of n people into these non-empty units. Now suppose we have this 1 till k. So we divided it into two sets, say 1 I and I plus 1 till k, right? So now what we are supposed to count first? So first we are splitting this line into some places. So one such composition is, I am saying, is this. I have split my line into like this, and then what is the second step? So we have this new set which is the set of intervals, set of the splittings, and then I have to choose a subset of this set. So if I want to choose a subset of this set, how many ways I can do it? So we have these two elements in this newly formed sets. So how many ways I can do it if I want to choose a set? Do you understand what I am saying?
Yeah. NC2.
So okay, yeah, NC2. No. So now my new set is this. A is equal to, this is one element and this is one element. So this is my big set. This big set has just two elements. So so if I want to choose a subset, basically it will be 2 raised to the power 2, right?
Yeah, 2 raised to the power 2.
So here you see, here your b, so yeah, so your bn is basically 2 raised to the power n, because n here refers to the number of lines, number of intervals, or you may say number. So bn is 2 raised to the power n. Do you get it?
Yeah, I'll go through everything once again.
Okay, yeah.
I joined late. So.
Yeah, yes. So yeah, fine. So I'll start. So I'll repeat this question again. So our question was, we have this n soldiers which were standing in a line. Then the officers, our step 1 was we split this line of n people into smaller non-empty units, and our step 2 was we were choosing a subset of newly formed units. So in the composite, so we see that we are talking about a line. Since we are talking about a line, and we are split, and the arrangement doesn't matter, we have to use ordinary generating functions, and also we have to use the compositions, ordinary generating functions and compositions. So C is basically b raised to the power ax. A is referring so an is counting, basically an is counting an is counting what is happening to each sub interval, and bn is counting what is happening to set of intervals. So we see that if we want to split a line into, if we want to split a line into various places, and second step was to choose a subset of newly formed lines. So in a way we are calculating, so first we are splitting the line. So we are calculating the, so split, if we want to split a line into non-empty places, we are and line has n people, we are basically counting the compositions of n. So we are, so splitting a line, so we can split a line in these many ways. Number of the solutions of this equation where each xi is greater than 0. Then to each line we are doing nothing, because so the coefficient will be just 1 1, and then if we have split our line into k, if we have split our line into k places, so we have distributed this n into two n disjoint intervals, say a1 ak. Now our newly formed set P is a1 ak, and we are supposed to choose a set. Now we are supposed to choose a set for this, and if supposed to choose a set for this, and since it has k elements, number of ways to do that is 2 raised to the power k. So basically we want to calculate this term, 2 raised to the power k 1 1 x1 plus xk equal to n, and we see that this is the closed form expression. So if we have this formula, if Bax, so if we compare it with this formula, this was basically x1 plus xk equal to n, ax1 till axk, and this was bk. So we see here since axi is equal to 1, so we get that an is equal to 1 for all n greater than 0, and a naught is 0 because each line has to be empty. So our first ordinary generating function is x plus x square plus xn and so on. So this is basically x upon, this is, so what is this? So if this is my ordinary generating function, what is this corresponds to? If I take x common, this will turn out to be 1 plus x square. And what is this term? If you want to write it in a closed form expression, so what is this series?
It's a GP 1 minus x raised to the power minus 1.
1 minus x upon, this is 1 upon 1 minus x, right?
Yes.
So we see that ax is 1. And now if we want to compare, so we want to compute the closed form expression of this. Now what is our bk? Bk is this, bn is equal to 2n for all n. So what is our bx? Bx is sigma 2 raised to the power n, x raised to the power n, and n is greater than equal to 0. And now what is this series? What is this series? This is also a GP, right? This is also a GP. This is 2x raised to the power
2x
n.
will come instead of x.
So this is 1 upon 1 minus 2x. And previously we discussed, like just now, that if we do composition BAX, this is our CX. If we do this composition, we'll get that C0 plus C1 x plus C2 x square, where coefficient of xn is n, and it was coming out to be Cn 2 raised to the power k sigma x1 plus xk equal to n, xi greater than 0. So we see if we compose B with A, we get our required answer. So now if we want to find the closed form expression, we use this ordinary generating function. So our Ax was coming out to be x by 1 minus x. Our Bx was 1 upon 1 minus 2x. So if we want to compute Bax, what is it? It is what we do, we basically replace x by x upon 1 minus x, right? This is the meaning of composition. So 1 minus 2 x upon 1 minus x, and we further simplify it, we get that it is equal to 1 minus x upon 1 minus 3x. So now this is our cx. We are interested in, this is our cx. This is our cx, 1 minus x upon 1 minus 3x. And our cn here was what we wanted to calculate, which is 2 raised to the power k, x1 plus xk equal to n, k xi greater than 0. So now once we have this, so we want a closed form expression of this. So cn is basically the coefficient of x raised to the power n in this series. So can we find out what will be the coefficient? So we can further simplify it. So what is 1 upon 1 minus 3x? Is it a well-known power series? 1 upon 1 minus 3x? 1 upon 1 minus 3x. So we used it earlier.
1.
Yeah?
1 plus 3x plus 9x square and so on.
Yeah, yes. 3x plus 9x square and so on. Now Cn is basically coefficient. So we want to find closed form expression of this, and Cn is the coefficient of xn. So, and this is also Cx. So what is the coefficient of xn here? So it is basically 1 plus, so if we further open it out, we will have that this is 1 plus 3 x plus 3 square into x raised to the power x square plus 3 cube x cube, so on, minus x plus 3x square, x plus 3x square plus 9x cube and so on. So what will be the coefficient of xn in this? So this is x raised to the power n, 3 raised to the power n greater than equal to 0, and this is xn 3 raised to the power, so if it is n, this is 3n minus 1, because this is 3 square and this is this. So now can you say what is the coefficient of x raised to the power n? So what is the coefficient of x raised to the power n here? It's 3 raised to the power n. And what is the coefficient of x raised to the power n here? It is 3 raised to the power n minus 1. So we see this is our series basically is this. And our Cn is 3 raised to the power n plus 3 raised to the power n minus 1. So is this fine how we are getting this? I can repeat any of the step that you need if it is not clear. So Anuj, is it fine?
Yeah, understood.
Okay. Is there, so somebody's saying something? Yeah. Okay. Okay. Now next question. Okay. Sorry. So now the next question is, a football coach has n players to work with a practice. So first he is splitting them into 2 groups and ask the members and then he's asking the member of each group to form a line. Then he asks each member of the first group to take an orange t-shirt, white t-shirt or a blue t-shirt, and members of other group are allowed to keep their red t-shirts. So in how many ways can all this happen? So first we split, so we have to count these ways. So first we split them into cases. So our first step is, so we have these n players. Our first step is the football coach, what he is doing, he is splitting these n people into 2 groups. And then second step is, that he is asking each group has to form a line. So basically arrange members in each group individually. Arrange members in each group. So so first step is n. So if we have these n people, then we are splitting it into into two groups, say A and B. So now, and the second step is whatever the people in A are there, we are arranging them in a line, and whatever the people in B are there, we are arranging them in a line. And the third step is member of first. So now members of first group. So here see, when we are saying the order of the groups are also mattering. So if A is my first group, so after splitting them in this, I am ordering the after splitting them into two groups, then the next step is that I am ordering these two groups. So A is my first group, B is my second group, and then he is asking, then so if A has some k, suppose A has some k people, some A1 AK, and B has some n minus k people, which is B2 Bn minus k. So first step was we have to organize them in a line. So we had to look at the permutation of A1 AK. Then second step was and similarly we had to do it for the second group. And the third step was is that member of so from the, if A is my first group, then each member has to choose a t-shirt, has to choose a color of t-shirt which is orange, white or blue. So each member has 3 choices here, and member of second group keep their red t-shirt. So members of second group has no choices. So first of all, since we are splitting them into 2 groups, and then we are applying something on first group and applying second something on the complement, we know we have to use the products. Now the thing is, which product do we have to use? Exponential generating functions or ordinary generating functions? So what do you think? So what do you think? So here we are dividing the set into 2 people. So here arrangement matters. So which type of functions should we use? Ordinary generating functions or exponential generating functions? So since we are dividing it into 2 groups, we'll use exponential generating functions. So what we are required to calculate? So what we are required to calculate, our step one is we are dividing it into, so we are our step one was partition 1 to n into ordered groups, partition n into ordered, partition this into ordered 2 groups. So we have to partition this set into 2 groups, and by ordering means so partitioning it into 2 groups, order matters. So if we have 2 groups A1 A2 and A2 A1, they have to be counted separately. So if you want to partition them into ordered 2 groups, it is basically same as choosing a subset of n, choosing a subset of this. So A1 basically corresponds to choosing a subset of this, and A2 is the complement. So, and in how many ways we can do that? We can do it in n choosing a subset of this is basically we can do it in these many ways. we have to we are choosing some I elements. So we are required, and then once we have divided this A1 AN into two groups, say A1 union A2, and suppose the order of A1 is I, order of A2 is J, order of A2 is J, what we are required to do, we have to arrange people of groups in a line. So first we did this, I going from 0 to n and choose I. Now first group has I elements, so it is, so we have, if we have to arrange them in a line, so it basically corresponds to I factorial, because if we have I people and if we want to arrange them in a line, it is basically a permutation which is I factorial. And second is we have to arrange the group of second people into a line, which will be J factorial. And then the third step was, and the third thing that the coach asked them was, for first group they have to choose a t-shirt from 3 colors. So they had 3 options. So so each member had 3 options. So we have this. And this, for the second group, it had just one option, which is 1 raised to the power j. So we have to compute this term and choose I factorial, 3 raised to the power I, j factorial, 1 raised to the power j. And we know that since we are using products of exponential generating functions, so what is our AX? AX corresponds to what we are doing to the first group. So what we are doing to the first, so AX is what we are doing to the first group. So what we are doing to the first group, first we are arranging them into a line, which is say n factorial. If we have n people, we are arranging them into a line, which will be done in n factorial way. And then we are giving them 3 choices, for each member has 3 choices. So which was 3, therefore we get 3n. And for second group, what we are doing to the second group is, again we are arranging them into a line, and then we are giving them a choice of 1 t-shirt, which is 1 raised to the power n, which is just 1, so which is n factorial. Now this is the product of, so now we have got these individual terms, and Cn will be, Cn is the required answer for n people, and it is the coefficient of x raised to the power n in Ax Bx. X raised to the power n by n factorial, because we are using exponential generating functions. So now what is Ax Bx? So Ax was n factorial 3n xn by n factorial. Bx was, Bn is n factorial, so n factorial x raised to the power n, n factorial, sum over n. Now if we further solve it, we see that this is sigma 3 raised to the power n xn, and this is sigma raised to the power xn. N greater than equal to 0, n greater than equal to 0. And this is basically, this is again a GP, which is 1 upon 1 minus 3x, and this is again a GP, which is 1 upon 1 minus x, Now we have this ax bx, and like earlier 1 minus x. Now once you have this, using your methods, you solve this, and you'll get. So once you solve this using partial functions, so you see that this is basically coming out to be 1 plus 3x square minus 4x. Oh, yeah. Yeah. So okay, sorry, we don't have to multiply it. Now we if we want to solve this, we do it like so. We break it down into partial sums. So we break it down into partial sums and then we solve it. So you solve this to find the values of a and b. Now we know what the coefficient here looks like, what the coefficients here look like. So you can find the coefficient of n. You can find the coefficient of n. So coefficient of n here will be, so once you have solved for a and b, this is basically a xn 3n plus b x raised to the power n. So this will be, you see the answer will be a3n. So we have a3n plus b, a3n plus b. So this will give you coefficient of xn. But we are using exponential generating functions. So coefficient of x raised to the power n by n factorial will be n factorial a 3 raised to the power n plus b. And I hope you know how to get this a and b. So your final answer will be this. So this was for today. So okay, bye.